polymerization is the action. It's the chemical process, the reaction that takes all those individual little monomers and forges chemical bonds between them to create that long polymer chain. It's the creation moment.
So how do we measure how long that chain is? For that, we use something called the degree of polymerization, and we usually just represent it with the letter N. It's really just a simple count of how many monomer units are in that final polymer. A higher N means a longer chain, and that directly affects the material's properties, like how strong or viscous it is. Now that we know how these chains are made, let's start sorting them into different categories. And the easiest way to do that is to just look at what they're made of. This brings us to homopolymers versus copolymers. This is a super straightforward distinction. A homopolymer, homo meaning same, is made from just one single type of monomer. Think of a chain of all red Legos. A copolymer, co meaning together, is made from two or more different monomers. Now you've got a chain that mixes red and blue Legos. Simple as that. And just to build on that idea, if you use 3 different monomers, you get what's called a terpolymer. It's still just a type of copolymer, but it's a more specific name for one made with 3 distinct building blocks, like having red, blue, and yellow Legos all in the same chain. All right, in our final section, we're going to see how this gets even cooler. With copolymers, it's not just about what monomers you use, it's about how you arrange them. And this choice of architecture can totally change the properties of the final material. First up, we have the alternating copolymer. This is the most orderly one you can make. The 2 different monomers, let's call them A and B, are placed in a perfect repeating pattern. AB, all the way down the line. That high degree of order leads to some very regular and predictable properties. Next, you've got the complete opposite, the random copolymer. As the name suggests, there's no pattern at all here. The A and B monomers are just distributed randomly along the chain. This kind of structural messiness often makes for materials that are more flexible and amorphous. Now, this one is really interesting. This is a block copolymer. Instead of mixing the monomers, you create these long sections or blocks of just one type and connect them to long blocks of another. This is incredibly powerful because the different blocks can have totally different properties. One could be hard and rigid, while the other is soft and rubbery. This makes them perfect for advanced materials like thermoplastic elastomers. And finally, we have the graft copolymer. The easiest way to picture this one is like a tree. You have a main backbone, the trunk, made of one type of monomer, let's say A, and then you graft on these side branches made entirely of a second monomer, B. This design is fantastic for creating things like high-impact resistant plastics. And that really brings us to the final big idea here. We've seen that you can choose your monomers, and more importantly, you can control their exact arrangement, alternating, random, block, or graft, to engineer materials with incredibly specific properties. So the question to leave you with is this. If you can be the architect of a molecule, what new materials could you design, and what problems could you solve?